Hey everyone, engineering statistics and linear algebra. Today we will discuss two important topics, that is subspace and a basis. All right, subspaces. I do read here the given statement. Let V be the some set of vectors, that is some subset of space with n dimensions, where Rn is a really indefinitely larger set of vectors, where each of vector has n components. In order for this V to be subspace of space with n dimension, it must be a subset of Rn. Let's understand each and every line. First, consider a space Rn. Let us consider a space Rn. It has vectors, all vectors having n components. So this is clear here. So Rn is a really indefinitely a larger set of vectors, where each of vectors has n components, that is drawn here. Okay. Next, let V be the some set of vectors. Some set of vectors, that is some subset of Rn. Subset of Rn means let me change the color here. Let me change the color. Okay. So uh, we have considered the space Rn. It has vectors, all are n components. Consider the set of vectors V. It has V1, V2, V3, and so on, Vn. All are vectors here. All are vectors. If I want to say the set of vectors V is a subspace of this Rn, this subspace of this Rn, first condition is it should be a subset of Rn. This is the meaning of this first statement. So I will write here the one more space. Can we call this as a subset of this Rn? Yes, it is subset of Rn. So we can call this as a space Rn for a set of vectors V. This is the meaning of the first statement. I conclude here. Consider the vector V. It consists of n number of vectors v1, v2, v3, and so on, vn. If I want to say vector V is a subspace of this Rn, the first condition is it should be first a subset of this Rn. All right. What could be the next? What could be the next a condition to say that the given set of vector is a subspace of n dimensional space? All right. Space is also known as a subspace. Either you can use space or subspace, one and the same in general. All right. Subspace is a subset that is closed under multiplication and a scalar addition. It should be a important definition here, which is basically closed under linear combinations. Linear combinations. These two operations keep output within the subspace always. The meaning of it is a subset of subspace Rn. It is a subset of a space Rn. In this space, only linear combinations of vectors should be there. What is linear combinations? Linear combinations can be v1 in c1 into v1 plus c2 into v2 plus and so on vn into a cn. Only these linear combinations should be there in this space. It should not come out of this area. It should not come out of this subset. So under this space, only addition and multiplications of v1, v2, v3 should be there. then only I can say that. Then only I can say that. So a set of vectors V is a subspace of this Rn. This is the second condition. All right. Based on these two concepts, let us we define a subspace. A subspace of a vector space is a subset that satisfies the requirements for the vector spaces. That is, a linear combinations stays in a subspace. Only linear combinations, not more than that. So the first condition is it contains a zero vector. In this area, in this region, we should find a zero vector. Next, if x and y are in a subspace, here we have taken v1 and v2. If v1 and v2 are in this subspace, then v1 plus v2 should be there in this region only. It should not cross this space. This is the second condition. That is, addition should be closed. All vectors should be closed under additions here. The third condition. If you multiply any vector x in a subspace by any scalar c, cx is a subspace as well. That means consider any vector v1, v2, v3 and so on. If that vector is multiplied with any a scalar value, it should not cross this border. It should not cross this border. If that is the case, means so we can say that a set of vector v is a subspace of this Rn. So as a conclusion, I can say that if I want to say a set of vectors v is a subspace of Rn, it should satisfy the following conditions. The first one is it should be a subset of this Rn, and it should have a zero vector, and it should if you do consider two vectors, addition of those two vectors should fall in the same region. And the fourth condition is if any vector is multiplied with any scalar value, then it should not cross this border. If all these conditions are satisfied for this set of vector, then we can say that a set of vectors v is a subspace of this uh, region, a space with n dimension. All right. With this, we will solve one example here. Let me change the color. Uh, all right. So next is first quadrant of xy plane. The first quadrant of xy plane, is it a subspace of R2? Is it a subspace of R2? Okay, I will show you. This is a complete Rn. This is a complete Rn as per the given statement. XY plane, x is varying from minus infinity to plus infinity, y is varying from plus infinity to minus infinity. In that reason, they are asking, is a first quadrant of xy plane, which is first quadrant here? This is a first quadrant. This is a first quadrant. Is it a subspace of this Rn? This is asked question here. All right. So what is first question? It should be what is first condition? It should be a subset of Rn. Yes, already. Yeah, it is a subset of Rn. It if it is Rn, so this is the reason. Obviously, the first quadrant, it is a subset of this Rn. Yes, first condition is okay. Holds good. What is second condition? It should consist of a zero vector. In the first quadrant, we do observe zero vector. Yes, all right. It is okay. The first condition is true. The second condition is true. What is third condition? For any values, for any two vectors, addition of those two should fall in the first quadrant. Should fall in a first quadrant. Okay, let me check that condition here. So first condition is true. Second condition, if we add any two vectors, vector A and vector B, the vector A is having two components a1 and a2. They are greater than 0 because first what we can say, first quadrant is considered here, and the value of B, and it should be greater than 0 in the first quadrant. If these two vectors are added, if these two vectors are added, they do fall in the first region only, first quadrant only. So that second condition is also satisfied. Let me clear you that point. Consider any vector. First quadrant means a vector A is and vector B. Consider two vectors. It has two components. Those two components should be greater than 0 because in quadrant number 1, x and y's are positive. If these two vectors are added, if any two vectors are added, like 2 3 is a vector 1, and 5 2 is vector 2. If these two are added, then it gives a vector 7 and 5. Again, it falls in a first quadrant. So that addition, uh, this reason the first quadrant is closed under addition. So that second condition is true. But what is third condition? Let me check. The third condition is, let us check any scalar. I have considered here c equals to -3 and the vector x is equals to 2 4. Here it is scalar, any real number. For example, I have considered it as a -3 and considered vector is 2 4 in the first quadrant. This vector should fall in a first quadrant. This c can be any real number. If these two are multiplied, the resultant vector is -6 and -12, but it is in third quadrant. This multiplication will fall in a third quadrant, -6 and -12. Let me clear you. Here the vectors are considered as 2 and 4. Vector 2 and 4 is considered, to which a -3 is multiplied. 2 and 4 means somewhere here 2 and 4. This is the vector considered. This is the vector considered. For this, a -3 is multiplied. So as a result, we'll get a -6 and a -8. -6 and a -8 somewhere here. This is the resultant vector, but it is in third quadrant, but it is not a subset of, it is not a subset of this one. It is not falling in a first region. So that the third condition is failed here. The third condition is failed here. So if any one of the condition is failed, then we can say that, uh, the first quadrant of xy plane, it is not a subspace of a space of two dimensions. I hope you have understood it. All right. Uh, let us consider the next example. S is a subset of some vectors. S is a subset of some vectors. That vectors are defined with condition here. It has x1 and x2 belongs to, this is the meaning of it. X1 and x2 are the vectors. They do belong to a region, a space of two dimensions, such that x1 should be greater than or equals to 0. Is it a subspace of, it is a subspace of space of two dimensions. So I do read it once again. X and y's are the vectors belongs to a space of two dimensions such that x1 should be greater than or equals to 0. So is it a subspace of R2? Okay, consider, write a given condition here. S is equals to x1 and x2 they do belong uh, a space of dimensions 2 such that x1 should be greater than or equals to a 0. Is it a subspace of a space of n two dimensions? All right. Now, what about the first condition? S is a set of vector lies in the first and fourth quadrants. How it comes? S is a set of vectors. It lies in first and fourth quadrant. The meaning of it is, so here only condition for x is defined. It should be greater than or equals to 0. That means here and onwards. It should be greater than or equals to 0. It should be this condition. From 0 to plus infinity. Complete this one. And for x2 they have not given any condition. It can vary from minus infinity to plus infinity, so that 0 to a plus infinity, a 0 to a minus infinity, but x is varying from 0 to plus infinity. That means the given set of vectors, they do fall in first as well as the fourth quadrant because of the given conditions. And they are asking, is first and fourth quadrant a subspace of a space of two dimensions? That is asked the questions here. What should be the first condition? It should be a subset. Yes, it is a subset of, it is a space of two dimension, and here first and second quadrant, so that it is a subset of the space two dimensions. Yes, it is okay. The second condition is it should have uh, what we can say, a zero vector. Yes, it is available. It consists of a zero vector. Then the second condition is closed under addition. Consider any two vectors. It can be 2 3, 2 minus 1. If those two are added, then obviously they do fall in first and fourth quadrant, for first and fourth quadrant only, so that first and fourth quadrant closed under a addition. Okay, what about the last condition? Consider any vector if it is multiplied with a minus 3, similar to the previous condition. If considered vector is 2 3, if it is multiplied with minus 3, then it falls in a third quadrant, so that the fourth condition is failed here. So that you can say that first and fourth quadrant, they are not a subspace of a space with the two dimensions. Let us we conclude here. Condition 1, it is satisfied because it has zero vectors. If you add any two vectors, they do fall in first and fourth quadrant only, so that condition 2 is also satisfied. But let us take any scalar. See here, the c equals to minus 3 is considered. A vector 2 and 4, they do consider. Uh, it is in first quadrant. If a scalar is multiplied to that vector, then the result is minus 6 and minus 12. It is third quadrant, so that condition 3 is not satisfied. As a result, the given set of vectors S is not a subspace of space of two dimensions. All right. Let you think by yourself. U is a set of vectors. It is a span. The meaning of span is linear combinations of given vectors 1 and 1. Is it a subspace of R2? Yeah. So answer for this is it is a subspace of R2. Conclude by checking all those conditions by yourself. All right. In the next video, we do discuss the definition of a basis. Right. So we do see in next video. And don't forget to like, share, comment on the video, and please subscribe the channel. We do see in the next video with a basis concept. Thank you.